Hi, my name is Alberto Pérez Rodriguez. I am an electrical engineering undergraduate student. I'll be presenting the research project titled Automated Power Supply Profile Generation Using a Power Amplifier, sponsored by Texas Instruments. The liaison is Steven Diwala and Fernando Lopez, and advisor Gladys Ducorroy. The motivation for this research project is that when building a waveform, which can be a time-consuming task, and you have to build multiple and unique waveforms that may include sinusoidals, ramps, squares, and triangular components, and other types of waveforms. The total number of waveforms can go up to thousands of different combinations to test voltage, temperature, or slew rates. This process will be easier to create, to read, and load the created waveforms, so there is minimal effort from the user to create all these combinations and use them for testing. The objectives of this research project. The first one is to create an NI LabVIEW VI, or virtual instrument, that facilitates the generation of arbitrary waveforms. This will include sinusoidal waves, ramps, squares, trapezoidal, or triangular waves, and randomly sweep through values on each parameter of the waveform. The second objective is to design an analog power amplifier. The third objective is to create a PCB design of this power amplifier. The fourth objective is to automate this process for loading the waveform on the National Instruments PSI function generator, sending the stimuli to the load, and reading back the output waveform data using National Instruments teststand. The objectives that have been accomplished are the VI to generate and read the waveform through the oscilloscope, and also the general power amplifier circuit for PCB. In process is yet to manufacture the PCB, redesigning the VI to be modular in order to easily run such programs in testnet. Validation testing for VI waveform generator and PCB board. In this image, we can see the VI, or virtual instrument, the front panel that was created to create or read a waveform, in which we can select to be each section a sine, sawtooth, pulse, square, ramp, noise, triangular, or a formula. We can select the dt, which is the time between each sample. When we are done setting each parameter, we can press done and select the file path in which we want to save the waveform. In this second image, we can see below the graph or waveform that was created using this program. As we can see, section 1, which is a sine, section 2, which is a ramp, and section 3, it is a DC value of 0, section 4, which is a sine again, section 5, which is a square, 6, a noise, and 7, a sine wave. As you can see, we can create many combinations of different waveforms, or even just one waveform, depending on which one we select. The selection criteria used to select the OPA 552 was that it had to be able to handle a load of 10 microfarads by 2 kilo ohms and had a slew rate of 5 volt per microsecond. We calculated the maximum current for the slew rate, which was 25 milliamps. So, and the selected op-amp is able to handle 200 milliamps and has a range of negative 30 volts to 30 volts. Based on the datasheet, the slew rate of the op-amp is 24 volts per microsecond. On the right hand side, you can see the PCB board design of the power amplifier, which is undergoing some adjustments to reduce trace lengths. The components that are going to be used in this board are through-hole components. This PCB will be manufactured to be able to validate the program of the VI using teststand. In this section, we can see the methodology that is going to be used for future test, which is going to be the feature/characteristic to be tested and approach and tools necessary, item pass or fail criteria, corrective actions when the test fails, expected data, actual results, and tested results are going to be part of the future testing. Feature/characteristic to be tested. The slew rate, offset, and amplification, using a basic waveform as the test input for the amplifier. The pass-fail criteria is the following. If the output meets the specifications, it fails if the output is outside of the range of acceptance. For the corrective actions when the test fails, the steps are as follows. We will verify the connection to the oscilloscope, verify the PCB connections, verify the wave generator output, correct the acceptance of the error, and verify. To test the OPA 552 will be the following. We will connect the op-amp PCB to the wave generator, load basic wave into the function generator, connect op-amp PCB to the PSI oscilloscope, observe the output waveform on the oscilloscope, do a comparison with the expected output waveform, then measure the values of the output wave and compare them with their theoretical values, which may be the slew rate, current, voltages, or others. Continuing with the steps for the OPA 552, we'll determine the pass-fail status given by the pass-fail criteria of the current test, make necessary adjustments, repeating the test if it's necessary, continue with the next waves with different amplifications. Once all these 6 tests in total have been declared passed, the power amplifier will be validated. And also, these steps will be the following for the test stand program or sequence with the VIs. This is the end of the presentation. Thanks for your attention. If you have any questions, please visit the link below and stay safe. Thanks.